Hello everyone. So we are in the tutorial class. So in this tutorial, we will be try to understand ionization, gas behavior, and Maxwell-Boltzmann distribution. So these are basically some aspects towards the foundation for plasma studies. Ionization is the first thing that should look into to create plasma, then how the gas behaves, and what is the distribution of the species that is there within the plasma. So we'll start with uh, you know ionization energies using cell model, and this we are starting in our school days, uh, where actually we studied our hydrogen atom Bohr model, and from there we could tell what will be the ionization energy. Now, apart from that, actually we don't know really whether we can use the same thing for ionization energy of other atoms. So, we will try to find that. So, using cell model, we will try to calculate the first ionization energy for hydrogen atom, nitrogen atom, oxygen and argon atom. Let us see how it goes. This is the first tutorial where using cell model of atom you calculate the first ionization energy of hydrogen atom. Okay. So, hydrogen atomic number Z is equal to 1, electronic configuration is 1s1 as you have seen there. So, ionization energy is the energy required to remove the single electron from the n equal to 1 cell, and by Bohr formula we will now all know that it is minus 13.6 Z square by n square. So, this is the nth energy level. So, the n is equal to 1, so and Z is equal to 1. So, we do have the ionization energy as 13.6 electron volt, and this is exactly the same with the experimental one. Okay. So, what we are getting here is that your theoretical calculation matches exactly with the experimental value. So, this one goes very fine with that. Now, we try to apply the same for another atom. So, what is that? Let us try with nitrogen. So, Z is equal to 7. Electronic configuration is 1s2, 2s2, 2p3. Outermost electron 2p3 of course, and n is equal to 2. The effective nuclear charge due to shielding by inner cell electrons 1s2 and 2s2, the effective nuclear charge can be calculated as Z effective to Z minus sigma 7 minus 2 is equal to 5 using Slater's rule. So, instead of Z equal to 7, we are taking Z effective as 5, and we are now trying to apply the same Bohr model to find out the ionization energy. So, it is minus 13.6 Z effective square by n square, and what we are finding that it is 85 electron volt. But the experimental value of ionization energy is 14.53 electron volt. So, there is a huge mismatch what you are seeing over here. So, the reason is that the simple cell model overestimates due to electron repulsion not accounted for. So, we see that even for nitrogen, this Bohr-like approximation, even with the shielding consideration, is not able to give you the right ionization energy. And what makes us to run after this ionization energy? This is because to form the plasma, the first thing that we require is ionization of the gas, and we need to know how much energy we would require to make the gas ionized. And what we are seeing here, that just using the Bohr-like approximation, we cannot get the correct ionization energy. So, this is one of the purpose of bringing in this numerical. Then we start for oxygen. Okay. So, atomic number Z is equal to 8. So, the electronic configuration is 1s2, 2s2, 2p4, outermost electron is 2p4. So, n equal to 2. The effective nuclear charge, again using Slater's rule, it is Z effective is equal to 8 minus 2 is equal to 6. So, now if we go for this ionization energy calculation using Bohr-like approximation, then what we are getting, E2p equal to minus 13.6. So, we have Z effective equal to 6. So, 6 square divided by 2 square is equal to minus 122.4 electron volt. But the experimental value is only 13.62 electron volt. This is again our estimation due to simplification that we have taken in here. So, again our Bohr-like model is not able to give the ionization energy. So, what we find that it is hydrogen-like configuration, it is giving us the correct value of ionization energy, but for other cases multi-electron atoms, because of the improper consideration of the shielding and repulsion, we are not able to reach the correct ionization energy using the simple Bohr model. So, that is not applicable in this case. For argon, you see that we have the Z effective, so Z is 18 and electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p6. So, I think it is correct, 6 to 8, 6, 14 and 4, 18. So, it is 18. Okay. So, this configuration is correct, and outermost electron is 3p6. Okay. So, n equal to 3 and Z effective is 18 minus 10, that is equal to 8. So, what we are getting is that, because the previous cell is having 6 plus 4, 10. So, ionization energy comes to be minus 13.6, 8 square by 3 square. So, it is coming minus 96.7 electron volt. So, this is again way of experimental value is only 15.76 electron volt. So, cell model overestimates the ionization energy due to neglecting electron correlations. So, what essentially these numericals in 9A to 9D tells that the Bohr's model, what we have learned in our school days, is applicable only for single electron system correctly, and for multi-electron systems it gives value which is not same as the experimental one, basically due to non-proper accounting of the electron correlations like electron repulsions and shielding like stuff. So, I just wanted to make it clear that do not try to apply the Bohr-like model to find out the ionization energy in multi-electron systems. Now, in this numerical 10, I just wanted to give you an idea about the kind of number density we are living in. For example, in this room where you are staying, what is the number density of atoms or molecules? Actually, I asked this question to many of my classes, and some of them are ready with the answers and most of them are not. So I thought that it is better to make you very much familiar with the kind of number density that occurs in and around us. So the problem is said like this: for an ideal gas at 1 atmosphere and 273 degree Kelvin temperature, calculate the number of gas particles per meter cube. So we are applying the ideal gas law. It is just to tell you the way we can find it out very easily. You don't never even need to remember it. Just if you remember what is the principle, you can just find out that number density in just a half of a minute, or like that. So what is the rule that we apply here? Ideal gas law that says that PV is equal to NKT. K is the Boltzmann constant, and what we are interested in, number of particles per unit volume. So it is N by V. So if you just change the sides, then N by V equal to P by kVt, as you can see from this relation. And you know that P is equal to 10 to the power 5 Newton per meter square, and then T is 273 degree Kelvin, as we have told here, and then kV is the Boltzmann constant. So we will all know what is the value. It is 1.38 10 to the minus 23 joule per Kelvin. So most of us actually remember these values: P of the order of 10 to the power 5, T 273, and Kb is 10 to the minus 23 order. So just if we want to know the order, it is not very difficult to tell you that it is 10 to the power 25. Then the factor about that you can calculate, but the number density order it can be told without much time. You can tell what will be the value of the order of number density. Okay, so you just calculate it exactly, P by K and T, then you get that it is coming to be around 2.69 into 10 to the power 25 particles per meter cube. So this is a huge number of particles. You see that we know 10, 100, 1000, but here what you are getting, 10 to the power 25 particles are surrounding you per meter cube. So insight is that plasma may form at much lower densities as well. When we are going for this cold plasma or low pressure plasma, typical densities are less than 10 to the power 20 per meter cube. So with respect to the density that we encounter every day, you can now compare the density of charged particles that occurs at cold plasma regime or glow discharge plasma regime, that may range from 10 to the power 16 to 10 to the power 20. When it is 16, 10 to the power 16, you can see that it is 9 orders of magnitude different from what is there in our room. And when it is 10 to the power 20 per meter cube, it is obviously it is 5 orders of magnitude less. So whenever you are going for such calculations or encountering a plasma, the number density when it appears there, you should have in your mind with respect to the density that you are feeling in your surrounding, how much low or how much high. So just give you a gut feeling. I just thought that this tutorial should be there to give an idea of the kind of number density of atoms in which we are living. So you may encounter this arc plasma which occurs at atmospheric pressure, which is a thermal plasma. There you can achieve a density of the order of 10 to the 24 as well. Okay. So, if you are able to fully ionize the particles there in the thermal plasma regime, then you may reach a density which is very close to that. When you are going to non-thermal plasma, if it is a very low pressure plasma, you can reach even 10 to the 16, 10 to the 17 per meter cube. When you are going for cold plasma devices at atmospheric pressure, there you can reach a number density around 10 to the 20 per meter cube as well. Okay. So, you see the range that in thermal plasma regime, you are able to get a density of the order of 10 to the 24 particles per meter cube. In the atmospheric pressure plasma jet regime, APPJ, you are getting a number density of the order of 10 to the 20 per meter cube. And in low pressure plasma, you can get a number density around 10 to the 16 to 10 to the 17 per meter cube as well. So, this now gives a clear picture about the kind of number density that may happen in your plasma, whether it is in lab or it is in atmospheric industrial area. You now have a clear idea about that. It can range from 10 to the 16 to 10 to the 24 particles per meter cube, depending on the kind of plasma that you have created. And this density of species will determine the process rate. So, what is the efficacy, what is the throughput of your process that you have designed will depend on the kind of active species that you have generated in your plasma, that very much depend on the kind of number density that you are generating. So, knowing the number density is very much important. Now, in this numerical, as I told you in the beginning, that we will be trying to know the distribution of the species inside a plasma. Now, as you know that in most of the cases, we will be approximating the distribution as a Maxwell-Boltzmann distribution in plasma, in thermal and cold plasma as well. But in cold plasma, many of the times there is a deviation from the Maxwellian, and you know that in non-equilibrium plasma, we say that the heavy species are in equilibrium at one temperature, but following the Maxwell-Boltzmann distribution, and the the electron species, they are following again a Maxwell-Boltzmann distribution, but at a different temperature. So, this is a kind of two temperature consideration, when one kind of species is following the Maxwellian distribution at one temperature, and the other species is also following the Maxwellian distribution, but at a different temperature. Now, in this problem, what is shown here, that so that number of particles in a gas obeying MB distribution in some velocity range V and V plus dV is function of speed only. This is a very interesting conclusion, that the number of particles is a function of speed only. Velocity is a vector, but C is a scalar quantity. It is square root of Vx square plus Vy square plus Vz square. So, now you know that the number of particles within velocity range Vx and Vx plus dVx, Vy and Vy plus dVy, Vz and Vz plus dVs can be written like this. Now, we know that speed is square root of Vx square plus Vy square plus Vz square. Then in spherical coordinate, the volume element whatever is there, dVx, dVy, dz, can be written as c square sin theta, d theta, d phi and dc. What you have to do now, you integrate over this theta and phi. Then what do we get actually? If you integrate our theta and phi from theta 0 to pi and phi 0 to 2 pi, as usually appears as usual for your spherical coordinate system, then after integration you get that this formula. So, 4 pi m by 2 pi k to the power 3 by 2 exponential minus mc square by 2 kt c square dc. So, this is the well known Maxwell speed distribution. Okay. So, we see that it is a function of speed only. So, this formula actually, although the c square term does not appear in the velocity distribution, it appears in the speed distribution only because of this integration that has been taken place. Okay. So, this is the last one, MB distribution at 3 different temperatures, T1, T2 and T3. So, when there is an increasing order, that T1 less than T2 and less than T3. So, this expression for most probable speed, mean speed and RMS speed, you can see that all of them are proportional to root over kBT by m. The factors are a bit different, and you have done derivation of this formula many times in your school and graduate classes. So, here I just calculate the most probable speed at 300 degree Kelvin for electron, proton and argon atoms. See, these are very common species that appears in plasma that you will encounter in your application areas. So, what you see here that I wanted to just bring out in this tutorial, so you start from 400 meter per second for argon atom. For proton, you see 1000 meter per second, rather around 2000 meter per second for the same temperature, the speed. And for the electron, it is, you see that 1000 if you take out, then there are 2 zeros, so it is 100 or 1600 meter per 1600, then 1000 meter per second. Okay. So, you compare, this is 400, then this is of the order of 1000 and this is of the order of 100,000. So, 100,000 and 100,000 when you switch from argon to proton to electron. So, this huge order of difference, they are not in just double triple, there is an order of difference in the speed when you switch from one species to another species. So, when you are encountering the species in plasma, you should have in mind that it is the mass of them which is causing so huge difference in their speed. The kind of speed you expect for different species inside the plasma, you should have your idea frozen from this tutorial that how they differ. There is an order of magnitude difference between this argon and this proton, and there are 2 orders of magnitude difference in speed when you are going from proton to electron. And when for the same species you go for increasing the temperature, I have plotted here one for 100 Kelvin, 1000 Kelvin and 1600 Kelvin, 11,600 Kelvin. So, that is your 1 eV, and 0.1 eV is around 1000, just take out 1 0. So, it is around 1000 Kelvin and 100 Kelvin. So, each time I have increased one order of magnitude in temperature, and you see the distribution, the way it changes, all are Maxwellian, but you see the peak height, how they change. This actually I generated from a computer program. So, as per the actual data, and the way it varies, it goes like this. So, you should keep in your mind the way the distribution varies as well as the velocity varies depending on the species. So, this tutorial clarifies you and frees in your mind the kind of velocity you may expect inside the plasma and how do they vary when you change the temperature and change the species. So, last one, this is if you want to write the Maxwellian distribution in terms of most probable velocity, you see the form that it appears here, it goes like this. Okay. So, It is interesting because many of the time you may require to write the expression for this distribution in terms of most probable speed. So I stop here for this tutorial, and we will go for the next tutorial in the next class. Okay, thank you.